Chapter 3.6, the derivative of logarithmic functions. So if we had a function like y is equal to log base a of x, what is dy dx? Well, in order to find this, we don't actually know the formula or the theorem to find the derivative, but we do know how to find the derivative of an exponential. So what I'm going to do is I'm going to change this right here to an exponential function. I'm going to find the a to the y is equal to x. A to the y is equal to x. And then what I'm going to do, of course, is I'm going to find the derivative of this. It's implicit differentiation is what I know now. I can actually take the derivative of this and the derivative of this with respect to x. Now, if that's the case, we get a to the y times the natural log of a, that's the derivative of this outside function a to the y, times, we're going to chain rule it, the derivative of that y, dy dx. And that's going to equal to the derivative of x with respect to x, which is just 1. So then what I get is dy dx is equal to 1 over a to the y natural log of a, right? And if you take a look, a to the y right here is equal to x. So I can even write this in terms of x. And it's as easy as that. We have the derivative of the log base a of x is equal to 1 over x times the natural log of a. Now, what does that example look like? Well, if here's log base 10 of this term, we want to find dy dx. So the derivative of y with respect to x is going to equal to 1 over x, so 1 over that input, 1 over that entire input, times the natural log of this 10. Don't forget, though, that we also have to find the derivative, the chain rule. I have to find the derivative of this inside. So I'm going to multiply that by the derivative of 2 plus sine x with respect to x is just cosine x. And that's pretty much it. This would be my answer. So 1 over the input times the natural log of that base. Next up, what if we had then y is equal to the natural log of x? Can you pause the video right here and try to prove this yourself? What would be the derivative of y equals the natural log of x, using the same method, except this time with the base of e? Well, hopefully you tried it, and the derivative of a natural log, you actually just get 1 over x. So let's try an example of that one. That one is a little bit easier, so let's try a little bit of a harder one. So when I see something like this, I no longer have to change this back to an exponential is what I'm saying, right? So this natural log of x plus 1 over square root of x minus 2, I don't have to change it to a logarithm, an exponential. I can just find the derivative straight from here. So dy dx will equal to 1 over this fraction, right, times the derivative of the inside, the chain rule. So 1 over this fraction right here, the input, times the derivative of that input with respect to x. And you will have to use the quotient rule here. Now what that will give me right here, it'll give me the reciprocal of this fraction right here, so I'll get square root of x minus 2 on top over x plus 1 times the derivative, and I'm not going to do the whole chain rule here because that's not the point of this video, but you will have to, the quotient rule, you will have to use the quotient rule here. Okay, but that would be the only difference, right? So, moving on. What else does it help you with? Take a look at this example right here. What is this? This is x to the 3/4. It's a product rule here. It's the chain rule inside. It's the quotient rule over here with an exponent of 5. So it's another chain rule here. Now that is a lot. That is a lot. However, using our log rules, our log laws, as you can see on the right side of the web page, you actually know how to expand this to look a lot easier. So everything that we've done before on this page, this can actually help you simplify finding the derivative of this hairy mess. All right? So what do I mean? Let's take a look. I'm going to take the natural log of both sides here. I'm going to take a natural log of both sides like this. Because what I'm seeing is the fact that I have a bunch of exponents here. This square root is going to be an exponent of 1/2, an exponent of 5. Logs are exponents. So it brings these exponents, multiple exponents, down onto the same level. And so what that helps us to do is we can actually expand all of this. So this product right here, this multiplication, I'm going to do natural log of x to the 3/4. I'm going to make it a sum of the natural log of that. And I'm going to change that square root into an exponent of 1/2. I'm dividing it by this denominator, which in the log expansion makes me subtract 3x plus 2, natural log of 3x plus 2 to the 5th. And then all of these exponents, like I said, I can bring it down to the same level as my natural logs because they are talking about exponents. Minus 5 natural log of 3x plus 2. Now take a look at how much easier this makes my life. Because the natural log of y is going to just be, the derivative of natural log of y is going to be 1 over y times dy dx. All right, implicit. This is just a constant, so I'm just going to get 3/4. The derivative of natural log of x is just 1 over x. So much easier. This is just 1/2 times 1 over this function, chain rule, times 2x. Right? So I just did the derivative of natural log of x squared plus 1. It's 1 over the input times the derivative of the inside, minus 5, just a constant. Derivative of this will be 1 over that input, and then chain rule it, multiply it by 3. That is really, really easy compared to using the product rule and the quotient rule and the chain rule here. So to simplify this, I get 3 over 4x plus, I'm going to cancel these, x over x squared plus 1, minus, multiply these, 15 over 3x plus 2. I did not take care of this y yet, so what I'm going to do is multiply both sides by y, which essentially we have right here. So that hairy thing does need to go into the equation, so I'm going to replace that y with this y in terms of x. So I'll multiply it by x to the 3/4, times square root of x squared plus 1 all over 3x plus 2 to the 5th power. And that's my derivative. So let's take a look at our next example. Well, when else can we use the derivative of a log or a natural log to help us? For cases that look like this, actually, to the right. Okay, but in order to do this problem, I'm just going to review this one real quick. The derivative of a to the x, if you remember the way we found it, it was an exponential because the exponent was the variable. We rewrote this to look like e to the natural log of a to the x, a being a constant. And these two were the same. These two are the same thing, right? Because the e and the natural log will cancel and you're just going to be left with a to the x. But why does that help us? Well, I'm going to rewrite it one more time. I'm going to bring this exponent down to the same level as the natural log of x. So I get x natural log of a. Now again, these are the same thing. All three of those are the same thing. And then we're going to find the derivative. Well, the derivative of any e function is the same function, right? Copy, paste, times the derivative of the inside. So the derivative of the inside, natural log of a, is just a constant, so it's natural log of a. And then, if you take a look, the natural log of x to the natural log of, e to the x natural log of a is the same thing, going back, as a to the x. So a to the x natural log of a. We're going to use the same idea to solve this one, to find the derivative of this one. So take a look at the difference here. There are a couple things to note. This is not a power function. That is not a power function because a power function has only the base is an exponent. Is a variable, sorry, not an exponent. Right? So this is the one like x to the second power, for example. Therefore, this is not going to equal, you cannot bring this down, square root of x times x to the square root of x minus 1. This is preposterous because we are not dealing with the same functions. Okay? This is also not an exponential function. Because what is an exponential function? An exponential function has the exponent as the only variable, right? The exponent is a variable, is the only variable here. So in this case, it would be like copy, paste, take the natural log of the base. So what you cannot do here, you cannot do copy, paste times the derivative of, I don't know, x or whatever it is. I don't know. That's just weird. We need a new method to solve. We need this because this is neither a power function nor an exponential. So what do? Well, we are going to change this in the same way as this. Well, what the problem is right now is that we have variable as the base and in the exponent. So what I'm going to do is I'm going to do the same thing. I'm going to rewrite that as e to the natural log of x to the square root of x. Right? Same thing. Again, I am dealing with the exact same thing. Same. And then I'm going to simplify this. What I'm going to do is I'm going to take that variable in the exponent and I'm going to bring it down to the same level as my natural log. So I have not yet found the derivative. So e to the square root of x times natural log of x. Now I'm ready to find the derivative. This derivative will be, this is now an exponential, right? E is a constant and I only have variables in the exponent. So now I can do a copy paste. Right? Times, chain rule, the derivative of this exponent. So the derivative of that exponent. All right, so now this original function right here is way complicated. Remember we had rewritten this before, so it used to be this, x to the square root of x. So I'm going to replace this with x to the square root of x. And then finish finding the derivative of this using the product rule. So it'll be the first times the derivative of the second, 1 over x, plus the second times the derivative of the first. I did skip a lot of work on that, so if you want to go back and finish that, you may. Simplifying this a little bit further, just because I see this is the square root of x. Let's multiply this by 2. This is half, so this will be square root, and this will go away. Again, I did skip a lot of work on this, so this will become 2 plus the natural log of x over 2 square root of x. And that would be the derivative of x to the square root of x. And that's it.